Okay, good. So we're set. Okay, let's begin. So, for those of you just joining, welcome. And where you're not, even though there's been 3 lectures before, we'll just kind of introduce things as needed for this discussion, where I'm trying to make it very self-contained. So don't worry too much. Okay, so the second law of thermo kind of has a reputation for being like notoriously difficult. It's actually a litmus test for the most part for scientists to determine, I guess, whether other scientists really know science, because it's such a core tenet to the field. But I'm going to try to explain in this lecture an approach to it that should make it hopefully kind of obvious, I would hope. Like it kind of just falls out from looking at certain systems and just kind of seeing naturally, yeah, I feel that would happen. And we'll kind of build up a case for plausibility, which is all you can really do for postulates, which is kind of what we've been covering. We've been covering the 4 main laws of thermo, but each one in itself is just a postulate. It's not really something you can prove or disprove. It's something that you can kind of believe in because you haven't seen it ever disproven. So that's kind of how postulates work. And you need them for a logical structure. You need to have postulates that you can build and deduce things from them and build kind of a model and a framework around them. So I wrote down my version of the second law, which is that the most probable stuff in nature happens. Duh. Which is really not very descriptive at all. It's not very useful, but it's gonna. I like to start off that way because I'm starting with the most simple one I can come up with. And when we actually analyze sort of the microscopic version of this macroscopic argument we're going to go through, we're going to see that molecules just do that, and it all comes out from that. And so it just makes sense that molecules move the way that's most probable, and then everything just kind of falls out of that. I also wrote down that through the power of abstraction, the second law can tell us why any change occurs. Yeah.
What's your favorite law?
This one. That's my face.
And longest.
The longest law?
I think it's really long.
It's really hard to get, but it's really awesome. Well, there's a big payoff in this lecture that we'll see. But so through an understanding of sort of spontaneous processes, it also tells you why time flows in one direction instead of going back. You know, why is there a past and a future? Why is that true? Why is there like an asymmetry in like time in our physical like world? And this is why. And we'll get to that. People have been following this lecture series. They're definitely going to be sick of this. But I'm going to write it anyway because it's so important. You've seen this 3 times now. This will be the 3rd. So I'm going to write, there's, by analyzing sort of some common experiments or some common like I've seen before, a postulate can't be proven or disproven, but it can be believed in. And so by showing some of the common experiments that have been done over and over and over again exhaustively and have never been proven wrong, the conclusion, we'll find that actually by believing in those, you can deduce, and like what fall out of them, of these 3 laws, are 3 properties that are in every thermodynamic system or in every physical system. And so I'll just kind of write those there. And we covered these in the last 2 lectures, but don't worry. We don't need to go into all the detail that those did to really get what's going on. So, the 0th law introduced something called temperature that kind of just fell out naturally of the idea that if I set up systems, I can tell that there's this thing in equilibrium thing in thermodynamics called equilibrium. And when systems are in equilibrium with each other, there's this natural transitive property which says that if A is in equilibrium with B, B is in equilibrium with C, then A is in equilibrium with C. That's always true. Even though you can't prove or disprove it, it is something that experimentally is always true, has always been found to be true. And that actually allows us to define something called temperature, which is kind of our measure of whether or not something is in equilibrium, specifically a type of equilibrium called thermal equilibrium. We'll find there's other things over here like pressure, chemical potential. When these are the same in systems, you have different types of equilibrium that are true. Like if pressures are the same, mechanical equilibrium is true between these systems. Temperature just fell out naturally as something, as a parameter, an indicator of this sort of thing called equilibrium. So the idea of equilibrium in thermodynamics was really kind of hashed out by this 0th law. And if you read the book on the chapter, it really goes into it. We don't need to go in that much detail right now, though. From the 1st law, we got something called internal energy. And this fell out of the idea that by studying the way this concept of, it's hard to do it without defining it using the terms that you're going to need to use. It's kind of cyclic, but there's a thing called energy, and it is this potential to do something called work. And work we'll define to be kind of moving like against a force through a distance. And if you take that to be the definition of work, energy then, the first law then tells you by studying the experiments, setting up the type of energy in a system and the types of transfer of energy you can have in or out of this system, there's a quantity called an energy that just naturally falls out of that. If you believe in that energy conservation, that energy is always conserved, that's the postulate. If you believe that postulate, then internal to energy makes sense because work and heat, which are the only ways of transferring energy in or out of a system, are because work it doesn't matter what path you take to put work in a system. There's different types of work. There's a thing called energy that can be qualified for every type of change you can have, or every type of state. Second law we're going to get to now is entropy. And it's a difficult concept, but we're going to find that entropy is a measure of disorder in systems, in physical systems. And we'll get to what disorder means. So, let's see. So that's kind of a recap. It's really hard to get, I know, because we spent whole lectures on sort of these individually. But all you really have to take away is that there's this thing called energy. It's conserved. There's something called work and heat. And really that's it. And we're getting to everything that's going to go into this guy. So, okay. So something that we kind of discussed in previous lectures but didn't really get into any detail at all was the idea that by looking at the first law and the second law, the first law is going to tell you about the quantity of energy in a physical system. But the second law is going to tell you about the quality. We'll get to what this means, this quality of energy. And it makes sense that the first law gave us the quantity because it told us, it was derived specifically from conservation of energy. It tells you there's this much energy in the system, there's this much transfer in and out. And so let's see. Let's just go a little deeper. The last thing I wanted to recap was work and heat, but we kind of already covered that. So I'm going to jump right into it. This is going to be all new stuff, and hopefully will be some nice self-contained kind of lecture. And at the end, there's going to be a big payoff. It's really cool. So let me just draw a little diagram. Might be hard for Evan, our people, but I hope not. So there's this thing that we went into a little bit in previous lectures, and it was the idea of your system. And your system is always some bit of the universe that you're really focused on studying. You're understanding exactly what energy there is, exactly what energy is going in and out of it. And there's this boundary that separates it from the surroundings, and that's the rest of the universe. So all in its whole entirety, the system and the surroundings together is the whole universe. And a boundary is really just an arbitrary distinction between this arbitrary system, this portion of the universe we really care about, which is arbitrary, and the rest of the universe. And we'll find that if you take this concept of work and heat that we kind of just went into really broadly previously, and in previous lectures, and even just a little bit earlier, by understanding what work and heat are on a microscopic level, which means macroscopic being at our scale, microscopic meaning molecules, at the scale of molecules, looking at what exactly they're doing and what they have to do to get this thing called work flow, or work energy flow, or heat energy flow. We're going to see that this is going to kind of start to give you an idea of disorder, and start to give you an idea of entropy transfer, and even what entropy is. So let's just go into it. So I'm going to show you two systems. They're a little abstract right now because they're just blocks. But I'm going to give you specific examples when we talk about them that should clarify things. So work transfer, as I'll get to in a second, is they're both defined. Heat and work microscopically are both defined in the surroundings. And the nature of that is the fact that within a system can't really determine where that energy came from, that it has in itself now. And it can't, because all energy is really the same. Like, energy can be converted from one form to another, but each form of energy is on equal footing with any other form. And that kind of logically, it makes sense that for a system, it can't have a distinction between heat and work energy inside of itself. You only have to think about its interactions with the surroundings, and this relates back to disorder. I'll show right now. So work is the idea that if I'm going to be transferring energy to the system through work, remember it can only transfer through work or heat to the surroundings. If I'm transferring it through work, what I'm really doing microscopically is I'm pushing every atom, all these atoms together in the surroundings, all together at the same time in a uniform way. So this is ordered, right? This is very pretty looking, it's ordered. It's, there's not that much randomness in it. If I can see where this guy's going, and I assume I'm in sort of an ordered array of molecules, I know where this guy's going. But the same is not true for heat. Heat, and I'll explain this a little more if it seems a little confusing, it's transferred by random motion of molecules. So it's kind of good to think of or associate work with order and heat with disorder, and we'll get to this when we talk a little bit more about entropy. Entropy can only be transferred into and out of a system through heat transfer, because this is necessarily random, this is necessarily disordered. Where if I transfer things by work, I transfer energy by work, the quality of my energy doesn't really deplete at all. It's all still ordered work to ordered work, or ordered stuff to ordered stuff. There's no really increase in disorder. I'm getting a little ahead of myself, but this is sort of the basic idea. There's order and transfer, and this is disorder. And just to really solidify this, and hopefully we'll get this concept, I'm going to go into just some actual physical example, one for this and one for that. So this idea, assume your system here, this is a piston. So as a piston is moving into the surroundings, it's pretty easy actually to transfer work in a very quality fashion, because the piston could easily just push with the surface of it all the molecules in a uniform direction based on just where the angle of that piston is when it's pushing. If we think physically of what this system is, we can think of this as one block of metal and another block of metal. There doesn't even have to be motion. There just has to be one hot block of metal and one cold block of metal. Now what does that mean for energy to transfer? If there's no mean motion at all, how is energy transferring? And the way we know this, or we can measure this, or understand it, is the idea that even in this system, there are molecules that are vibrating around kind of randomly. They're actually, in a crystal, it's a lattice of atoms, and they're jiggling around their equilibrium position. And they're sitting there, and as they jiggle around, if it's hotter, they jiggle faster. And if it's colder, they jiggle slower. So what does that mean at the boundary here? Well, I'm transferring heat because these guys are jiggling a lot, these guys are jiggling a little, and this guy jiggling a lot will hit one of the guys jiggling a little and make it jiggle a lot. And then that guy will jiggle and transfer to its higher friends. And what ends up happening is even though there's no mean motion, you get transfer of energy by energy kind of flowing up this way. Whereas with work, you had to have motion against an opposing force. Motion, you have to actually have things moving to transfer work. Heat doesn't even need motion, like mean motion at our scale. Things could be sitting there and not moving at all. But we know, understanding that there are molecules there, that the energy can still be transferring from one to the other. So by understanding sort of the microscopic view of work and heat, we're already starting to dig into a little bit of this idea of order and disorder in systems. So let's see. Boop, 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 boop. I'm doing pretty well. I'm not even have to look at my notes. Okay, awesome. So let's move forward. And by all means, ask questions. If anything's confusing, if I said a word that you don't know what it means, I might have just slipped up and not have known that it was one that we had defined previously or something.
Shaun, does it,
Yep.
as it's heating up, when it jiggles, it's jiggling at the highest rate possible. As it transfers the jiggles to other molecules,
What do you mean
it's gonna
highest
slow
rate
down.
possible?
Well, isn't it going to slow down as it hits the cooler?
It will slow down, and that's how it loses its heat. It's some of its energy, right? It's transferring its energy away, and it's becoming cooler because that really fast jiggling guy right on the surface with the colder guy, or the colder block, it's going to knock the other one, make it move fast, and then naturally, to conserve energy, it has to move slower. You can't have energy just kind of come out of nowhere, so it's going to give its energy up at like a molecular level.
At some point, it reaches some sort of
Equilibrium,
right?
bingo. If there's no boundary in place, or barrier in place, which you can kind of see, this is confusing yet, I don't have to get to it yet, but what's up?
I think you might have kind of answered my question, but don't you think eventually they'll all run out? I mean,
So this
they
is
might
the
not
secret
run
of
out.
temperature, right? Everything's jiggling, even this table, everything's always jiggling. And that's kind of something we'll get to in the next lecture, which is the third law, which we haven't really talked about much yet. But the third law tells you you can't get to something called absolute zero. And absolute zero, what would that mean? If I had a block of metal and I had no temperature, what would that mean?
There's no...
They're not jiggling.
They're not jiggling. And if I haven't proven it yet, but the next lecture will prove that if there's no such thing as absolute zero, you can't reach it. So therefore, everything has to jiggle, to some extent. With higher temperature, you jiggle more. Does that make sense?
Yes.
Cool. Okay, so let me move on. So this is kind of leading into this really great payoff of honestly the entire course, but mainly this lecture in particular.
Nothing. She just ate ice and didn't like it.
Nobody likes cold. So it's the idea that power in science springs from abstraction. And this is something that's hard to understand. Like, there's such a thing as a breakup in the scientific method of hypothesis and experiment. And you can set up an experiment and understand it very well and get data and really understand this physical system. But if you don't put any effort into abstraction, you're never going to build up a framework to understand and predict things about systems you haven't yet touched physically or set up physically to look at. What's up?
In your body, does your brain jiggle most?
Every single atom, even the little molecules in your neurons are all jiggling around. Maybe not the neurons itself, but the atoms definitely are.
The fastest? Your brain jiggles the fastest?
No, not necessarily. Depends on the temperature, right? What's up?
Do your bones jiggle?
Yeah. Everything has atoms, right? Everything has cells as atoms. In your body, at least, everything has cells.
Or you'd be dead?
Or otherwise, you'd be at zero, at absolute zero. We'll get to that, though.
What if you had no atoms?
What if you had no atoms? I guess I'd wonder what you'd be. You'd be empty space.
Would you die?
You wouldn't really be living. We'll actually get to what living means. I mean, and entropy helps to define what living actually means, which is cool. Let me just move on, though, because there's quite a bit of stuff. So power in science springs from this abstraction, this idea of abstraction. And the great abstraction from the second... Oh, what's up?
Does dark matter jiggle? Yes.
Oh, no. So I don't know much about dark matter, but I would assume if it's... Actually, I don't think so, because dark matter might not be made of atoms, and atoms are what we know to jiggle, so I don't know. Maybe not. I don't know.
Do black holes jiggle?
But
doesn't everything have?
What is a black hole? Let's see. Black holes are...
It's something that creates...
Black
Smear
holes...
jiggles.
Black holes are like are what's called a singularity. It's a bunch of mass at one point, which is really hard to understand. But I think outside of it's empty space, so no. I think outside of that pinpoint is empty space, right? I don't know.
Isn't there a smear on it? All the information is smeared in the front of a black hole?
That gets confusing too, because it's like really where is matter, and that's kind of a quantum mechanical thing, and that might get blurred a lot with the black hole stuff.
There's an event horizon.
That was this guy, which is just imaginary. And it's not like a physical thing. All it is it tells you when you go into a black hole, you can no longer get out of it again, and it all depends on the amount of gravity at that point there. So it's not really a physical thing. It's like a thing. Let me get back on topic just so we can wrap up on time. So the great kind of abstraction that comes out of this lecture is the second law, considering it, and most of thermo, is that all of our actions, from digestion to acts of artistic creation, are at heart captured by the essence of the operation of a steam engine. Weird, right? Doesn't seem to make any sense. Seems totally fake, right? I'm going to prove this to you, though. Hopefully you guys will follow along. I don't sound too crazy. So let's get into this. So I'm going to draw right now an abstract version of a steam engine, and I'll explain what the physical version of the steam engine is like and how it gets abstracted into this. So this is an abstract steam engine, and it's called a general heat engine. And as I'll get to in a second, just to give you a little bit of an intro, a heat engine, all a heat engine does is it takes heat and it converts it into work. It takes energy that's in the form of this disordered random motion and it turns it into ordered motion. So we'll get to this. We'll get to all of this, but this is something that's at hot temperature. It could be fuel combusting, it could be nuclear reaction, it could be just a hot piece of metal. Anything hot. Here's something cold. That could be the surroundings of your system. That could be, what's up? Oh, hi, sorry. So this could be the surroundings of your system. This could be a bunch of ice. It could be anything colder than the hot temperature guy. What's up?
Does the H stand for hot and the C stand for cold?
You got it. This is a subscript too. You know what a subscript is?
What's the T stand for?
Temperature. Sorry. That's temperature cold, temperature hot. So there's two reservoirs, or not even necessarily reservoirs. There's, they need reservoirs. There are two things. One's hot, one's cold. And there's going to be heat transfer from the hot thing to something else. And there's going to be heat transfer from this thing to the colder thing. These are always going to happen. This has to happen if there's no barrier in between. There's no insulation or something. And what this magical thing is just any device that turns this heat transfer going through it into work coming out. So this is an abstract heat engine. All of us are this. Everything is this. Everything doing any change is this. And we'll get to why. But when I told you we're all kind of an abstract steam engine, a steam engine is really just hot steam moving through a turbine and ejecting it out to the atmosphere. So that is sort of the abstraction of a steam engine into this heat engine, this general model. So let's explore a little bit the experimental postulates kind of underlying the second law. And they were actually framed originally in terms of steam engines, in terms of a heat engine, because it kind of all came about during the time. This guy named Carnot actually came up with something I'm about to get to. Yeah, and that's, he did it because he wanted to help France out. He wanted to help France beat all the other countries by having the better steam engines, by having the better energy generation in his country. So that's kind of the birth of all of thermodynamics, which is kind of cool. But let's get into it. So I think I covered all this. Nice. Awesome. And okay. So the efficiency of this heat engine is defined by the ratio of the work you get out to the heat transfer you're putting in. So if I had a perfect heat engine, you'd have to have all of this heat going in, being converted into work, and none of the excess heat going into here. We'll find that this isn't true, and that's, in essence, the postulate. That is the thing that we can't prove or disprove, but have never seen happen in a system we've ever set up or observed. So this efficiency... I'll go through another example. If you have so much heat energy coming in, and half of it gets converted to work, and the other half gets shot out the back to the what's called the cold reservoir, or cold sink, then that's 50%, right? That's half of that, 50%?
You know, like the barriers that you use for your heater so it doesn't transfer to cold. Is the barriers heat the steam engines?
Barriers, steam. So they put in a steam engine, they put barriers in place so that heat goes through to the turbine, right? You have like steam to the turbine. They put barriers up so none other goes out this way. They don't want that. Is that what you mean?
I'm talking like about if do those transfer?
Mm-hmm.
I think she wants to know if they're what is it called?
Are the barriers?
The containers are
the barriers
didactic? There's a word for it that he mentioned.
Do you mean like in the earlier chapters, the thing about the vacuum sealed flask?
Wasn't
Right,
I getting that though? That
Yes,
the thing's
the
insulated from the rest
insulated
of the surroundings so
Right.
that you have it transfer the way you want? I don't know. Well, let me get through this and then I'll talk to you after and we'll make sure that you get it. So the cool thing is that guy named Carnot from France, he actually, in order to better France, he derived a remarkably simple expression that actually tells you the maximum theoretical efficiency you can ever get out of a heat engine. And it looks like this. It's called the Carnot efficiency. And if you're an engineer, like a mechanical engineer, you know this really well. And I'll explain why. And it's 100%. And you subtract off the ratio between those two. That's all you have to do. If you can abstract whatever your engine is, whatever your steam engine, nuclear reactor, whatever, into this model, this is going to tell you the max possible efficiency. And it's usually 50-60%, which goes to tell you how hard it is to get good energy.
So you just take your system and measure the two temperatures?
Yep. And usually you have to do some averaging, but that's all you have to do. But not to say that you're ever going to reach this. This is the maximum perfect ideal. I guess that's better. So the cool thing, and why I was saying the power of science comes through abstraction, is the idea that if you understand this, you'll understand that no matter how perfectly designed your steam engine is, you're only going to get some percent of this. You're never going to get all of this. This 60%, whatever it is, you're only going to get up to 55, maybe 30%. So that tells you a lot. That gives you a lot of power. It tells you, I don't have to try to really design this thing better and better and improve the efficiency. I already know the limit. I just have to see how much of that I can get. And that's the only way to change it, is to really change, like lower the temperature you eject heat to, and maximize the temperature of your source. That's all you can. That's all you can do. So let's see. And to have 100% efficiency, you either need to be ejecting your heat to absolute zero, which we know to not be possible. We'll prove in the next lecture. Or this has to be at infinite temperature, which also doesn't make much sense, right? And that just comes out of that being infinity or that being zero, and mathematically that becoming one. So there are two classical statements of the second law, using the framework of this conceptual heat engine, and let me just take them. So let's just look at them. These are things that people made a long time ago, back in the era of steam engines. These are their statements. This is how they said this is the second law. There's something called the Kelvin statement by Lord Kelvin, some famous scientist dude, and there's one called Clausius statement, which is by another famous scientist named Clausius. So the Kelvin statement is that no cyclic process is possible. This is just something they've never observed, and we've never observed since. It's possible in which heat is taken from a hot source and is converted completely into work. So that's one way of saying the second law. This is another way of saying the second law. Heat, and this is one that's more familiar, heat does not pass from a body at lower temperature to one at a higher temperature. But you can if you have an accompanying change elsewhere. And a famous example of this is a refrigerator. A refrigerator is taking something hot and is transferring something from something cold into something hot. Into something hot. But in order to do that, it needs work. It needs power. It needs to be plugged in. So that's the caveat. Is you can do it. You can defy this, what's a spontaneous process, which we'll get to, but you have to add work in. You have to pay for it. And just another way to restate this guy is that nature kind of exerts a tax of conversion between heat and work. So some amount of heat put into the system by the source has to be brought into the heatsink. You can't have, a heat engine doesn't work without the heatsink, is basically what this guy's saying. Which is kind of, you don't originally think of. You don't originally think that in a power reactor, some plant, the cooling towers are the most important thing, not the turbines, the big fancy things they spend a ton of money on. Okay, just a note on the spontaneity of processes, and we can move right on to the big climax of the whole course and this lecture specifically. So a note on spontaneity. So spontaneous process, it just means that it can be driven without doing work of any kind. Nature, it's natural in the sense that nature just does it without having to consult anybody. You don't have to put work in the system. And another important thing, because of sort of common use of the word spontaneous, it doesn't mean fast. Some people they think that because of the way it's used in everyday language, but in science it's a very precise meaning. Spontaneous just means the tendency for something to happen without work being inputted in. It's not necessarily fast or slow. Two spontaneous processes. One is the expansion of a gas. If I had a gas in this little container and I opened it and it fills the room, that's spontaneous because I don't have to put work in and it's fast. But diamond is actually spontaneously converts into graphite. Right? Graphite?
No, coal to diamond?
No, well you can do that way, but you have to put work in by pressure, right?
Oh, right.
But no, yeah, diamond into graphite. Diamond naturally or spontaneously converts into graphite, but it takes hundreds of years. It takes a long time. So that just kind of separate the idea of rates being associated with this, because thermo can't talk about rates. It doesn't have that information, as we talked about in the very first lecture. It doesn't have that information. What's up?
I thought it was impossible to transfer coal to diamond.
No, you can. I can take coal and I can push really, really, really hard on it, and if I get the crystal structure to push into the right one for diamond, it becomes diamond. But it's going to want to naturally come out of it over years, over hundreds of years.
No.
It'll be clear again. It'll be clear because of the optical properties come from the crystal. Okay, so with that little note in mind, the Kelvin and Clausius statements of the second law are both summaries of just sort of exhaustive observations. As I said over and over again, they're scientific postulates. They're not really proven or disproven, we just believe in them. And that we can build a logical structure around them. It's actually more elegant to express these statements in terms of a natural thermodynamic quantity. Just as we saw with the zeroth law and the first law, entropy is going to naturally bud out of the unification of these statements into one more sort of elegant statement. And you can actually prove logically that this implies that, or the falsification of that implies the falsification of that, and vice versa. So these are logically equivalent. They're just different takes on the same thing. And this one I'm going to say now is identical to both of these, but is its own kind of take, interpretation, and that actually pops out entropy, and it makes more sense. So it's really hard to do the math to show this, so I'm just going to go ahead and use an analogy. And from the analogy, we can get a qualitative understanding of what entropy is, and we don't need to worry about the details. And realistically, we don't. If you have an intuitive understanding, you don't really have to go that far. So this is my analogy, and it's actually from the book. And actually, Monero made up a cool one too that I'll say before class. So there are two rooms. There's a library, there's a quiet library, and there is sort of a busy street. Busy street. And the analogies here is this is a system at low temperature. This is a system at high temperature. Now, there's one more analogy I'm going to add to both of these systems. I'm going to sit in the middle, and I'm going to sneeze. And that sneeze represents a transfer of heat. So this is a transfer of heat. And we don't have to worry about work, remember, because work is already ordered. Introducing work into a system or out of a system, not going to change the entropy. Heat does, because heat is transferred via disordered, chaotic, random motion. So a sneeze in a library, what do you think that's going to do? Is that going to be really disruptive? Is that going to be not so disruptive? Probably more disruptive than a sneeze in a busy street, right?
Yes.
So through this analogy, you can kind of understand that by transferring heat into or out of a system, depending on the temperature of the system you're dealing with and the amount of heat you're transferring, you can kind of get the idea that entropy, this idea of entropy, which we're going to get to right now as a measure of disorder in nature, is proportional, which just means it goes up as the quantity of heat goes up, heat transfer, right? The bigger the sneeze, the more disruptive it's going to be in either of these, no matter what. But it's also what we say is inversely proportional. Don't worry about the math, I'll just explain it, to the temperature of your system. So that says if the temperature is really high, my entropy, my sneeze isn't going to be as disruptive. And you don't really even know the powers. You don't have to worry about any of that. But it's just the idea. You get the idea of that as heat is transferred into or out of a system, it either adds a lot of entropy or not so much entropy. And it all depends on the temperature of the system and the amount of heat you're really transferring. So with this in mind, we're ready to express the second law in terms of the entropy, which is this sort of measure of disorder. And it actually captures and encapsulates the Clausius and the Kelvin statements. And this is it. This is the second law, and you should know it and repeat it and tell all your friends because it's awesome. This is the second law. The entropy, and I still have yet to really say what that is, of the universe. Actually, no, I don't, because it's the disorder. It's the amount of disorder that you bring into or out of a system. You can changes in entropy, all associated with that sneeze analogy. The entropy of the universe, which is both surroundings and your system, and this is an important distinction I'll say right after, increases in the course of any spontaneous process or change. Same thing. So, what is this really saying? This is saying disorder in the universe is always increasing, never not increasing. It can say the same sometimes, in very special cases. What's that?
So say a cold drink, just if you drink a cold drink, does that mean your body is going to become colder?
If you drink the cold drink, your body will definitely become colder in the sense that I'm going to drink the drink, it's going to go down all the digestive fun stuff, and along the way, because it's colder than 98.6 degrees, whatever internal body is, my body's going to want to put heat into it as it goes through. But as it kind of sits in my stomach, it's going to kind of sit there for a while and just kind of equilibrate. It's going to cool things down a little bit. But
and then it's going to hit equilibrium too.
Yep, and then I think invariably, because conservation is, energy is conserved, the amount of energy you put in when you drink is just going to kind of be added into the whole system, because it takes a while to get rid of it, right? And eventually you do get rid of it, but it gets muddy as to where the energy went. But because it gets like digested and all that weird stuff. So the key word here is universe. So I didn't say that in a system or in surroundings you have to have your entropy always go down. You can have your system have its entropy decrease. But if it's going to do that, it's rejecting heat out of it and stuff, it's getting rid of disorder, and where's it putting it? In the surroundings. So all this is saying that if your system is going to decrease in entropy, your surroundings better increase enough to be overall bigger. You have to always, the universe has to always be increasing this disorder. So here's the climax. This is the big payoff to the whole course and to this lecture specifically. Climax. All right. The first law, conservation of energy, and its other the form we brought it into, and the internal energy. Boop, boop, boop. Identify feasible change among all conceivable changes. And what does it say? A process is only feasible if it conserves energy. So it tells you what's feasible in the universe. The second law, and the entropy, identify the spontaneous changes among these feasible changes. And a feasible process is spontaneous only if the entropy of the universe is increasing. So this is a lot of abstracted, this is a lot of truth, general truth in the whole universe, and everything, in psychology, biology, physics, chemistry, everything. It's saying the only changes that can happen are ones that conserve energy, and the only ones that can happen without any work being added are ones that increase the entropy of the universe. And you can have ones that aren't spontaneous, but you have to add work. And you know exactly how much work you have to add, because of this guy. So that's almost everything that you really have to even think about when you're thinking of things changing. And I didn't really, a lot of people who are new didn't get to see it in the very first lecture, but I kind of showed all the possible frameworks in physics and what governing principles you can kind of use. And thermodynamics uses grabs a lot of them. That the only one it doesn't grab that really matters is one that has information containing rates. So it doesn't tell you how fast things are going to happen. It just tells you the tendency. Like, is it even possible? Yeah. Is it spontaneous? Yes or no? That's all I can tell you, but that's a ton of information for not that much work. So there's one great conclusion I'll end with, but I'm just going to have one little thing in the way. And it's the same approach that's used in the book all the time, and it's the one I like to take. And it takes what we've been studying has been classical thermodynamics, which is the idea of thermodynamics is approached only from a macroscopic perspective. We can derive all of this, and it comes out of these postulates from things that are scales. Thermodynamics doesn't even know about atoms. It doesn't even believe in them. We only enhance our understanding by having confirmed experimentally that atoms do exist, and by deriving from the atomic perspective back up to thermo. What was I saying? Okay, so now I'm going to get into what is entropy on a microscopic level. And this actually helps you know what entropy is. Before it was like, what is this thing? Why is this thing always maximizing? This tells you why. There's more information contained in doing from microscopic up than from starting at the top like we did. So this, I'm going to start not using the one using energy levels because they're so weird and they confuse people, but I will get into that in case people were like, just for a second, if people did pick it up or wanted to know more. It all comes down to this guy. And it's such a freaking cool equation that I totally have it tattooed. Because it's awesome. And actually, it's a specific case, but don't worry about that because it just gets more complicated. But the main thing it's telling you, and this is something derived by somebody called Boltzmann. And what's really sad is Boltzmann was a really brilliant scientist, super ahead of his time. He did all this stuff assuming atoms. He did all of statistical thermo, all that underpinning of thermo, assuming atoms, when people did not believe him that atoms existed. They resisted him so much because they did not believe atoms existed. And he actually, I'm not going to say the conclusion of his story, too many kids, but poor guy didn't have a happy life. What's up?
I thought Einstein was the one who found...
He confirmed them experimentally through something called Brownian motion. I'm surprised you know that, actually. How do you know Einstein was associated with all that? Like, did all that? Whoa. We'll get to that though. So all this is telling you, this is on his epithet too. This is Boltzmann's formula. It's absolute entropy in a system. It's just a proportionality constant. No real meaning there. It just gets it in the right units. It is a natural log, which don't even worry about that is. It relates directly to something called microstates. The number of microstates. And a number of microstates is, say I have a box, I have some amount of energy in it. A microstate is I look at that box this is a macroscopic perspective. I look at a microscopic perspective, and I look to see what are all the atoms in it, and how many times can I count swappings of those atoms without being able to distinguish that as a separate state. So all that's saying, for this certain amount of energy, say I have a gas of things bouncing around, it's saying how many things have the exact right kind of velocity, moving, the right position, where I can sit there and grab those two and swap them out. So say maybe this guy is doing that too. I swap them out and I can't tell they're different. I can't tell the whole state's different. How many times can you do that? And does that make sense at all as a measure of disorder? That's telling you that if I can do it a lot, if I can make a lot of swaps, and I can't tell that I can't really tell that I made a change by looking at the whole thing again, that's a lot of different options everything has in it to do something. And if there's only one swap or there are even no swaps, then I kind of know where everything is. And so the one that has more of these things, swaps that you can make, that's naturally more disordered. It's kind of hard to grasp. I have let me say something I wrote down because that might help. Okay, yeah. Let me more explicitly state like the